So now we're going to look at the maths of standing waves. And let's start with two fixed ends. Now, if we consider the length of the string, we can then build a relationship between the length of this string, or the length of this standing wave, and the wavelength. Now, if we consider the node here as the starting point, we can see that an entire wavelength would be twice this length, or that this is half a wavelength. As we increase the number of nodes and antinodes, or we go up a harmonic, this is our first harmonic, our second harmonic, what we can see here is that the relationship is that the length L is equal to the wavelength, right? And as we increase the number of nodes and antinodes to our third harmonic, what we can see is we have a wavelength and a half inside this length L. Now, if we consider the relationship between wavelength and length, then it should make sense that wavelength equals 2L over N. Let's have a look at our harmonic, see if that makes sense. Here, where our harmonic is N equals 1, then our wavelength is equal to 2L, yes. Our wavelength when our harmonic is N equals 2 is 2L, right? So length over 2 would give us a wavelength equal to L. That's if our harmonic is 2. That was a bit long-winded, that last one. Okay, so what happens when we have our third harmonic? Well, if we consider that we have 1.5, the way that I like to do it in my head is if I take L and I divide it into 3, 1, 2, 3, I've got 3 half wavelengths. And so one wavelength would be equal to L divided by 3 and then multiplied by 2, right, to give me wavelength. And that 3 that I've divided L by happens to be the harmonic, right? So N equals 3. And you can apply that to here as well. If I divide L into half wavelengths, there's 4, and then I multiply it by 2, right? And that would give me the length of one wavelength, which happens to be 2 over 4, half a wavelength. So let's have a look at the same thing, but this time for two open ends, right? So very, very similar, because if we have a look at the length of our standing wave, let's have a look to see what the relationship between this length and a full wavelength is. Well, if we look at this green line, I would need another quarter of a wavelength there, or a quarter length string, and then here I would need another quarter, which gives me a half. So basically what that's saying to me is that this is half a wavelength. So therefore, I would need 2 L's to give me, or 2 lengths to give me one wavelength. So the wavelength equals 2L. Our second harmonic, same thing, as in 2 fixed ends. What you can see here is this is an entire wave, right? So that wavelength is equal to L. And now I'm on my third harmonic, right? So you've got 1, 2, and what I'm going to do here is I'm going to divide the half wavelengths. So that's 1, that's 2, and that's 3. So if I divide this length by 3 and then multiply it by 2, then I get my full wavelength, right? Which is 2L divided by 3. Okay, and so the relationship is the same. The wavelength equals 2L over N. Now, where this gets a little bit tricky is with open at one end. Now, with one fixed, one open, you end up with this strange situation with our simplest form being the first harmonic. Our next is the third harmonic. So we've got an interesting relationship with our N there. And then our next one's our fifth one. So if we have a look first simplest situation, our first harmonic. Our length L gives us basically a quarter of a wavelength, right? Because I would need this, and then I would need another quarter, and then another quarter, and then another quarter, right? So I would need 4 lengths to give me a wavelength, an entire wavelength. So that gives wavelength equals 4L. Now, if I squeeze another harmonic in there, it'll take me straight to the third one. And what I've got here is 1, 2, and 3/4 of a wave. So if I split, how can I do this? I'm going to take this length and I'm going to split it into, 3, right? So L over 3 gives me a quarter of a wavelength. So if I now multiply this, which is L over 3, if I multiply it by 4, I'll get an entire wave. So lambda equals 4L over 3. 3 being the number of our harmonic. Similarly here, we have a length for our 5th harmonic, which includes 1, 2, 3, 4, 5/4. So let's split that length into 5, and you've got L over 5. And now if I multiply this L over 5 by 4, 1, 2, 3, 4, I've got a full wavelength. So 4L over 5, which means that my general formula, look, it's 5 and it's the 5th harmonic. So my general formula is 4L over N, right? N is the number of harmonic. Now, remember, this is only odd for one fixed, one open. Now, these formulas are not on the data booklet. You either learn them off by heart or you derive them. Now, what do we do with all this information? Well, there's 2 things that you can be asked to do. The first one is to consider the frequency, right? And the frequency will depend on the wavelength. So therefore, you simply take whatever wavelength you've calculated using these relationships and you apply it to the wave speed equation. Remember, speed equals frequency times wavelength, right? So F0 equals, this is our fundamental, remember fundamental would be for your first harmonic, and then increasingly it would, your frequency will be dependent on the wavelength of whichever standing wave you're being asked about. So always divide the speed by the wavelength. The second thing you have to consider is speed. Now the speed of the wave does not change in any of these situations because the speed of the wave depends on the medium. If it's air, if it's metal particles, if it's traveling through wood, if it's traveling through water, these are the things that affect the wave speed. So if you are changing this frequency to increase the number of nodes and antinodes, the speed will be constant. And that's usually the basis for most numerical questions. Right, so I think that's it. You have your 3 equations and it's time to practice.